Welcome. This is the fifth and the last lecture of the MSI Advanced Topics in Plane Geometry. So today I'm going to talk about Ptolemy Theorem and its applications. I guess most of you have already known what Ptolemy Theorem is, but there are a lot of applications and interesting corollaries that are related to the ME exam and maybe USMO exam. So we start with a brief introduction of Ptolemy Theorem. Ptolemy Theorem is a relation between the four sides and the two diagonals of a cyclic quadrilateral. It was discovered by the Claudius Ptolemy, a Greek mathematician, astronomer, and astrologer, geographer, and music theorist about 2,000 years ago. He lived in the city of Alexandria, which is in Egypt. Okay, so one more thing. For the topics, we'll talk about Ptolemy Theorem, Simpson Line, and another topic is Kelvin Transformation. Kelvin Transformation. Okay, so let's start one by one. So in the following picture, ABCD we call it is a cyclic quadrilateral in the sense that the four vertices A, B, C, D are on the circle. Okay. In general, for any triangle, there's a unique circumscribed circle, but for any quadrilateral, it's not necessary there is a circle that passing all the 4 points. So for those 4 points can be sitting in a fixed circle. It is called the quadrilateral is called a cyclic quadrilateral, or in another word, we can say that A, B, C, D are concyclic. Okay, so the assumption is quite weak, and the conclusion is strong. So we know that we assume that ABCD is a convex quadrilateral, and then the multiplication of the diagonals AC and BD is equal to the sum of the multiplications of the two pairs of the opposite sides. AB times CD plus AD multiplied by BC. Okay, so let me talk about the proof. The proof is quite interesting. Of course, we use similar triangles to do the job, but there's some techniques there so that you will use different criterion to determine the pairs of similar triangles. Okay, so here's the idea. So we define a point K in the interior of AC. So let's pick up a point K. So how to define such a K? The point such a K is defined so that ABK, so this angle, is equal to DBC. So we just pick up a K so that these two angles are the same. So you can say that BK and BD are we called isogonal lines with respect to triangle ABC. But anyway, we just pick up K. We don't need to use the concept isogonal conjugate, even though that we can use that concept to prove something. Actually, we can use that to prove the Ptolemy Theorem. Anyway, so once you do that, we can quickly see that there's a pair of similar triangles. Triangle BCD is going to be similar to triangle BKA. Why? Because these two angles are the same, and these two angles are the same because they are facing on the same arc length. So by the inscribed circle theory, these two are the inscribed angle theory, inscribed angle over the same arc length. So they must be the same. So between these two triangles, there are two pairs of angles are the same, so that these two triangles are similar. Once they are similar, you will have the ratio. So AB over BD is equal to AK over CD. And that can be used to prove part of the theorem. If we do the cross product, so then we will get AB times CD is BD times AK. So very good, because this AB and the CD appears here. Okay, so the trick part is that we want to use another ratio to prove there's another pairs of triangles that are similar. Okay, or maybe not in this situation. So But in the later we will talk about the Ptolemy inequality. Then we do. Okay, so let's see. These two angles must be the same because both blue angles are the sum of the black one plus the common angle KBD. This green angle is equal to that green angle for free. And therefore, we have another pair of similar triangles, namely KBC and the ABD. They are similar because they have two pairs of angles, corresponding angles, to be the same. So then we can have another ratio. So BC over BD is equal to KC over AD. So we do cross product again, we get, very good, another pair of multiplication. AD times BC, that's equal to BD times KC. Okay, so let's add these two up. So then AB times CD plus AD times BC would be equal to BD times AK plus BD times KC. So you can factor out the BD. So you are left with AK plus KC. But from the picture, we will see that AK plus KC is AC. So that gives a very good proof. I like that proof. It's pretty straightforward, but yet it has some techniques. In particular, this is a good exercises in using similar triangles to prove theory. Okay, so if we use a little bit more trigonometry, so then it's even easier because the quadrilateral is sitting in a circle. And once something in a circle, we can use the law of sines to actually compute all four sides. Okay, so assuming that R, capital R, is the radius of the circle, so then we can use law of sines. So as you see, we mark the alpha, beta, gamma there. So let me change the color. So we actually try to compute all these sides in terms of R and the corresponding angles. So the first one is AB is 2R times sine gamma. So this is sine gamma. So for this triangle, we use law of sine. We can use that triangle as well. The law of sine says that each side is 2R times sine of the opposite angle. So we have that. So similarly, BC is 2R sine alpha, which is okay. We can do that. And the CD is equal to, that's a little bit complicated because this is the angle. And so this angle would be, we know that this red angle plus beta plus alpha plus gamma would be equal to 180 degrees. So this red angle is 180 degrees minus alpha minus beta minus gamma. So that will give us 2R sine alpha plus beta. So we computed AB, BC, CD, and the DA. So DA is simple. DA is 2R sine beta. Good. And how about the two diagonals? Well, we can use law of sine again. So AC is equal to 2R times sine. This is AC. And so it's equal to that. And that angle is 180 degrees minus alpha minus gamma. But in terms of sine, they are the same. So 2R sine alpha plus gamma. And the BD would be beta plus gamma. So what is BD? So this is BD. Okay. And this angle is gamma. But this angle is beta because they are the same inscribed angle. So BD is that. So if we put everything together, we will see that the capital R can be cancelled. And we are left with this identity that we need to prove. Okay, because everything is turned to the sine of some angles. And so this equality is equivalent to the Ptolemy Theory. And why this is true? This is simply from the so-called the product to sum rule. Let me try to interpret that. Maybe we have, we probably need to use some trigonometry. Let's see which one is the best to compute that. So I can actually list the series. Sine alpha, not use sine alpha. Sine x, sine y. is actually equal to half of cosine x minus y minus cosine x plus y. So that's the formula. And if we use that formula in a smart way, we can turn the left to the right. Well, so the easiest way is, so both sides are product, and I can basically turn to sum and subtraction for every one of them. Maybe we can do that. So the left-hand side is, by the formula, is half of cosine, the subtraction, which is alpha minus beta, minus cosine, the summation. Summation is alpha plus beta plus 2 gamma. But alpha plus beta plus gamma is already 180 degrees, so it's that should be the left-hand side. And we can simplify it. It's half of cosine alpha minus beta and then plus cosine gamma. So that's the left-hand side. So let me use a different color to compute the right-hand side. So this is the left-hand side. So for the right-hand side, the first part is sine alpha sine beta. So this is half of cosine alpha minus beta minus cosine alpha plus beta. But then we will use triangle angle theory. Alpha plus beta is 180 degrees minus gamma, so it's half of cosine alpha minus beta. So plus is plus cosine gamma. Subtraction is alpha minus beta. Addition is alpha plus beta plus gamma, so it's 180 degrees plus gamma. Both should be equal to, how come that's the, yeah, so maybe I cosine beta, that's plus cosine gamma, that's true. So this one is also sine is cosine, their plus, their subtraction is alpha minus beta, their multiplication is 180. And there's nothing wrong here, but what that proves these two are the same. Let me try the last one. Sine gamma, sine alpha plus beta plus, oh, how come sine alpha plus beta plus gamma, that's 0? I computed wrong. CD, let's say CD is obtained. Oh, okay, sorry. Alpha plus beta plus gamma is not equal to 180 degrees. I made a mistake here. So the previous one is correct. So here we have, yeah, so cosine alpha plus beta plus 2 gamma. That's how they add up. Sorry, alpha plus beta plus gamma is not equal to 100 degrees. It's not 3 angles. But then this is cosine alpha plus beta, and it's not cosine gamma, so just leave it as minus cosine alpha plus beta. So that's good. So the last one is half of cosine alpha plus beta, that cancel, minus cosine alpha plus beta plus 2 gamma. Okay, so if you compare, you add these two together, you cancel the cosine alpha plus beta, and you basically leave the same one here. I cannot use plus, this is negative. And you put the last two, you add the last two together, you get the first one. Okay, so that's the proof using trigonometry, and it's the easiest in the sense that we just need to use. Number one, we use law of sines. To turn it to a trigonometric identity. And then number two, we use product to sum formula to prove it. And if you think about this, you actually can use that to give another proof of the product to sum formula in trigonometry. And in fact, this Ptolemy theory is equivalent to all the trigonometric formulas, like sum formula, product to sum formula, sum to product formula. It's equivalent to all of them. You can use Ptolemy Theorem to give the proofs of all these trigonometric identities. Okay, so this is my favorite. I just want to make some applications of Ptolemy Theorem. Some of the applications are actually trivial, but you will see that they are interesting. So the first example is a problem, popular problem in Euclidean geometry that says if you have an equilateral triangle inscribed in a circle, and if you take any p and on the point, any p on the circle, then from this picture, the conclusion is PA is equal to PB plus PC. There are different ways. So one way to prove it is, I believe I can use the geometric proof would be I draw 60 degrees. So that PB would be equal to that, and the PC is equal to that because you can prove that these two triangles are similar. There are similar triangles. Anyway, I'm not going to talk about the pure geometric proof. I'm going to use Ptolemy Theory, and it becomes a one-line proof. So we know that BC and AP are the diagonals, so we take BC times AP. That's equal to AB times CP plus BP times AC. That's Ptolemy Theorem. However, AB is equal to BC is equal to CA because this is an equilateral triangle. So if we cancel AB, BC, and CA, then we will get PA is equal to PB plus PC. So that's a nice proof. Okay, an even more trivial proof is that, more trivial application is that this actually, Ptolemy theory is actually equivalent to the Pythagorean theorem. Okay, so in this case, we just need to extend the right triangle to be a rectangle. So if we have a rectangle ABCD, the Ptolemy theorem basically say AC times BD is AB times CD plus AD times BC. But we're working on a rectangle, so AB is equal to CD, so AB times CD is AB squared. BC is equal to DA, and the ABC times DA is square again, and the AC is equal to BD. Two diagonals are the same, so that gives us AC squared. So that gives the Pythagorean theorem. So Ptolemy theorem implies Pythagorean theorem. Okay. So this is the second example I would like to mention. So the third one is, people say this is called the Einstein proof of Pythagorean theorem. I would say I don't believe Einstein was the first one to prove it. But the nice part is that we use a little bit the similar triangle. This gives us the simplest way to prove the Pythagorean theorem. Namely, we all know if I have a right triangle and I take the height, so then how many triangles are there? There are 3 triangles. And for all the 3 triangles, they are all similar. So suppose this is A, this is B, this is C, this is H, this guy is X. So maybe I should draw a better picture. So this is, and I draw it line here. So let's say this is A, B, C, H. This is X, this is Y. So what you will see is that A squared would be equal to CX. So by the similar triangle theorem, because the smallest triangle is similar to the biggest triangle. And you have B squared is equal to CY by the same reason. So therefore, A squared plus B squared is CX plus Y, that's equal to C squared. So that's the proof. We're using similar triangles properties. We are able to do that. And so the nice part I want to point out is that this is actually the same idea in the proof of Ptolemy theory. Once again, if you extend your right triangle into a rectangle and draw a circle to it, so the fact that you draw the height in this special situation happens to be that this K is the K in the proof of the Ptolemy theorem. Why? Because this angle, because this is the right angle, this angle is equal to that. But this angle is equal to that. So K is the same K as in the Ptolemy theorem. So this so-called Einstein proof of the Pythagorean theorem is just the same proof in the proof of Ptolemy theorem, which we try to construct the point K and construct the 2 similar triangles. Okay, so of course the proof here is more general, But in the special case, that would give us the proof of Pythagorean theorem. That's the point I want to make, and which I think that's interesting. All right, so my next favorite topic is, how about if the 4 points are not concyclic? So that means if I have an arbitrary quadrilateral ABCD. Okay, so this time things is a little bit interesting. So of course we don't have the Ptolemy Theorem, but we have the Ptolemy Inequality. It turns out that you can still talk about the product of the diagonal, and you can still talk about the sum of the product of the two pairs of opposite sides. Okay, so they may not be equal, but at least you have the inequality. You know that the first one, AC times BD, is not more than the summation of the other two. And the equality is valid if and only if A, B, C, D are concyclic. Okay, so if you think about this, you would try to use the same idea in the proof of Ptolemy Theorem. How? Well, this time you will see that I still want to construct the point K. But unfortunately, that point K is not going to be on the line AC anymore. So what's our construction? Our construction is I will pick up a point K. So number one, I still want this angle to be that angle. So in the previous proof, well, I just need to draw a line, and that line hit AC, then I define K. I cannot do this anymore. So I will just extend it to the point so that forcefully I want triangle ABK to be similar to the triangle DBC. So I want these two triangles basically to be similar. I can always do that because the one angle is the same, and I extend this so that the corresponding sides are proportional, then I'm done. So this can always be done. Okay, I shouldn't erase that. And so the difficult part is that I can make these two triangles are similar, but the difficulty part is that, so how to prove the other two pairs of triangle are similar? So delta KBC should be supposed to be similar to ABD. Okay, why? So in the previous one, we can use the fact that, well, once these two green angles to be the same, then of course these two blue angles are the same. But that's only one angle. Right. Previously, we can use inscribed angle theorem to say, okay, this angle is equal to that angle, but they are still the same. But how to prove that? Okay, so let's first just write down something. As before, we first construct. We can take a K so that AB over BD is BK over AC. So because of this. So then we will imply that triangle ABK is similar to triangle DBC. Okay, that's fine. And we will see that this is useful because you can take cross product to get AB times BC equals something else. Once they are similar, then we can rewrite this equation as the following. So AB divided by BK is equal to DB divided by BC. So just take a look. AB to BK, if we write this, AB over BK is equal to BD time over BC. So you see, this is exactly, say, these two triangles, ABD and KBC, the corresponding two sides are proportional. And we also have that fact that the two blue angles are the same. So that's by I forgot what criterion called in congruent triangle. This is called the SAS. This time it's what it is. One angle are the same. The other the two sides form that angle. The side lengths are proportional. So these two triangles are similar. So once they are similar, then we have AD times over KC is equal to DB times BC. Very good. So taking cross product of this, we will get of this one, we will get this. taking cross product of that, we will get that. So AB times CD plus AD times BC will be, okay, you can still factor out the BD times AK over KC. And the nice part is that we have triangle inequality. AK plus KC is greater than equal to AC, so that means it's greater or than or equal to BD times AC. Okay, so that we proved the Ptolemy inequality. And so why in the equality case that ABCD has to be concyclic? Well, in the equality case, that means the triangular inequality become equality. And when they become equality, so that means KAC is not a triangle anymore, because triangle inequality, say AB plus two sides, is strictly bigger than the third. So the only situation is when K happens to be on the point AC. And if K happens to be in the point of AC, so then we can quickly see by the similar triangle that this angle is equal to that angle. And if these two angles are the same, so they are facing the same chord. So we know that by the inscribed angle theory, the inverse inscribed angle theorem, that ABCD has to be concyclic, or in other words, the quadrilateral ABCD is a cyclic quadrilateral. All right, so I like this a lot. So this is called the Ptolemy inequality, which is even more general than the Ptolemy Theorem. It's quite general. It can be it's just for, it states that for anything this is true, basically. For any quadrilateral, this is true. Okay, so that's the first topic. The second topic is that I want to introduce a transformation which will tell us why all this method will work. So here is the idea. In mathematics, if it's too easy to get a conclusion, or you can use different ways to prove the same theory, maybe you can have 20, like the Pythagorean theorem, there's more than 200 different proofs. So that would imply that there's something secret, there's a deep reason inside the theorem. And that's true for Ptolemy theorem. I'm going to tell you that both the Ptolemy theorem and the Ptolemy inequality are not more than the fact that it's equivalent to, Ptolemy inequality is equivalent to triangle inequality. Ptolemy theory itself is even easy. It basically stated the following. So suppose x, y, z are collinear, assuming that they are on the same line, then xy plus yz is equal to xz. So this is an easy trivial statement everybody knows. You don't even have to know geometry before you know this. But Ptolemy theory is just equivalent to this simple fact. And how can we see it? Well, we will need to introduce something called a Kelvin transform. So to start, a Kelvin transform carries with a fixed point O and a positive and an R, a constant. And where O is called the center of the transformation and R is called the radius of the transformation. So for any point P on the plane, I can draw a line and I define the point P prime, okay, in that direction, so that I want OP times OP prime is equal to R squared. And as you can see, I can always do that. So I'm not going to go to the other side. You can define negative Kelvin transform, that's fine. Everything is on one side only in my lecture. And the OP times OP prime is equal to R squared. And that is called the Kelvin transform because essentially for any point P, you can find the P prime. Okay, so remember this line is obtained by just connecting OP and extend it. Okay, you can quickly see some special cases, like if a point P is inside the circle, this is the circle of radius R, then you will see that P prime has to be outside the circle. And the closer the P to the O, then the further the P prime, because OP times OP prime has to be fixed. So OP is close to 0, OP prime has to be close to infinity. And in particular, when P is equal to O, there's no Kelvin transformation. But you can also think that the transformation of P is to infinity. Okay, so this is the first observation. The second observation is, of course, if P is outside the circle, and the further the P go away, then its Kelvin transform goes back to the interior of the disk of radius r. Okay, so if for any P on the Euclidean plane, there's a corresponding another P prime on the Euclidean plane, such a assignment is called a transformation. So there are a lot of transformations in geometry and in mathematics. For example, the easiest transformation you already have seen is the translation. Okay, if you move your stuff from one point to the right by one step or to top 5 steps, so that's called a translation. Okay, it's a kind of transformation. Another transformation you have encountered is the rotation. You probably have learned in analytic geometry, so you can rotate everything in the Euclidean plane counterclockwise by a fixed angle. Let's call the angle to be alpha. And this is another kind of transformation. Essentially, other than the point O, every point in the Euclidean plane can be transformed to another point in the Euclidean plane. Okay, you can think about they are not sitting in the same Euclidean plane, they are sitting in different Euclidean planes. And so then the Kelvin transformation send a point in the first Euclidean plane to another point in the second Euclidean plane, and that's called a transformation. So think about two Euclidean planes are two universes. Okay, they don't have any relation to each other. So any transformations provided a messenger that's sending the information of one universe to the another universe. So that's my explanation. And later we will see that if we create two Euclidean planes, on one Euclidean plane we play with Ptolemy Theorem, and on another Euclidean plane we produce some trivial stuff like triangle inequality and something like that. They are the same. They are equivalent. And we will quickly see. All right. So cotangent to Kelvin transform, there's a concept called the anti-parallel line. Okay, so suppose ABC is a triangle. We know that I can draw a line which is parallel to BC. Well, the line does not even have to have a reference triangle. Any line, you can have another line passing through one point. You can have another line to parallel to the original line. So this is called the fifth postulate in Euclidean geometry. And so the anti-parallel line, which proves to be very useful, it's that the definition of it has to depend on a fixed triangle. Outside the triangle, any line, you cannot simply say this is an anti-parallel line. That does not make sense. So what's the definition? So here, in this situation, we will see that E and F is an anti-parallel line. If the following is true, AF times AB is equal to AE times AC. So why we call this anti-parallel line? Because if AF over FB is equal to AE over AC, if they were true, then the line obviously should be parallel to BC. And if you replace division by multiplication, then you call the anti-parallel line. For anti-parallel line, triangle AEF is similar to triangle ABC. For parallel line, AFEBC. The triangle AFE is similar to triangle ABC. Here, triangle AEF is similar to ABC in the sense that these two angles are the same. So another way to define the anti-parallel line is that we just want these 4 points to be concyclic, because once these two angles are the same, the 4 points would be concyclic. Okay, very good. So why this is useful? So this is useful because of this equation. And you can reinterpret this equation. Let's say this is R squared. You can reinterpret this equation as that E and F are the Kelvin transforms of C and B respectively, right? you send C to E, so this guy is equal to a fixed number R, and this guy is equal to another fixed number R. So that's E and F are the Kelvin transformation of C and B respectively. Okay, so now how to interpret using the idea of Kelvin transform to interpret the Ptolemy theorem. So everything is in the following picture. All right. Oh, okay. I forgot one thing is that we can actually use the similarity to actually compute the length of CE. So let's say AF times FB is equal to AE times EC. And we assume that the Kelvin transformation radius is equal to 1. We assume that equal to 1. And we know that this will give me AF over AC. Sorry, this is AC is equal to AE over AB. So therefore, the triangle AEF is similar to triangle ABC. And once they are similar, you have EF over BC. That will be equal to AF over AC. And so therefore, you can compute the EF in terms of AF over AC times BC. You're not completely satisfied with this formula, so you use the fact that, okay, so I wrote a lot of mistakes here. AF times AB is equal to AE times AC. So AF is the reciprocal of AB, so I just write this as AB negative 1 BC over AC. So this would be equal to BC over AB times AC. So that's EF. So remember, EF is the product of AB times AC, BC divided by AB times AC. Okay, so here let me do Kelvin transform. So ABCD is on the circle. So what I'm going to do is I will use A as the Kelvin transform center and 1 as the radius. The radius is the choice of radius doesn't matter. You can choose R equal to 100. That's fine. And let's do the Kelvin transform of C, B, and D respectively. So in the picture, I already marked C prime, B prime, D prime. So C, B, D are the Kelvin transform of C and B and D. And so what I want to prove is that this B prime, C prime, D prime are collinear. They are on the same line. Why? Well, if you look at this triangle, you would realize that this angle is equal to that angle. Because this is Kelvin transform basically produce anti-parallel lines. Fine. And by the same reason, you would see this angle is equal to that angle. Very good. And whether or not B prime, C prime, D prime are collinear is that whether or not these two angles add up to 180 degrees. And now you know that these two angles summed together is equal to 180 degrees because A, B, C, D are concyclic. Okay, very good. So B prime, C prime, D prime are on the same line. And by the above formula, we would see that B prime, C prime is equal to BC times AB, AC. So that's what we have. And the CD would be C prime, D prime will be CD, and the BD, some computation. And we will use the basic fact. The basic fact is B prime, D prime is equal to BC, B prime, C prime times C prime, D prime. And if we have that, we can put all these together. And if you multiply AB, AD, AC on both sides, you will get Ptolemy theory. Okay, so this gives another nice proof of the Ptolemy theorem. But what we have more? I have more to do the comments. Okay, so on one side, you see, everything is a setup. Everything like we take a Kelvin transform of BCD to B prime, C prime, D prime. These are the setup. Okay, as I said, you can think about this scenario in the following way. on one side, on one you have two Euclidean plane. On the first Euclidean plane, you are teaching the Ptolemy Theory. On the second Euclidean plane, you just teach the same, the trivial formula that B prime D prime is equal to B prime C prime plus C prime D prime. And they are equivalent because of the relation. Okay, so on one universe is a complicated, maybe exotic theorem, it corresponding to the other universe. That is a trivial theory, and so they are equivalent. So Ptolemy theory is only difficult on surface. Using the same method, actually, you can use that the same method means Kelvin transform to prove the Ptolemy inequality. Okay, so I would like to end my lecture by introducing another nice way to prove the Ptolemy theorem. And with the introduction of another way to prove it, I would like to introduce another interesting thing in Euclidean geometry called the Simpson line. And so in the following picture, ABC is a triangle inscribed in the blue circle. And let P be a point on the blue circle. So then let me draw the perpendicular line from P to A, B, B, C, C, D. Okay, for example, X is we call the paddle point of P to the side BC, and the Y is P projected to CA, and the Z is the projection of P to AB. Of course, the projection Z is on the extended line of BA, but that's fine. And the conclusion is that these 3 points, X, Y, and Z, are collinear. I keep saying concyclic. They are collinear. So this line plays a very important role in triangle geometry. It is called the Simpson line. And so this is named after Robert Simpson, but he was actually not the one proved the theorem. The theorem was proved by Wallace. Discovered by Wallace. Okay, but somehow Wallace was forgotten, and we named the line to be Simpson line. How to prove it? Well, the proof is actually quite simple. So we want to prove that X, Y, Z are collinear. So essentially, because A, Y, C is collinear, they are the same line. And in order to X, Y, Z to collinear, we just need to prove this angle is equal to this angle, right? And so by the fact that PZAF, AY is concyclic, because I have these two right triangles, they add up to 180 degrees. So therefore these two angles, these 4 points are concyclic. So I know that this angle is equal to this angle. Very good. And so the second brown angle, by the same reason, would be equal to that angle. Okay, now we are done, because let's consider 2 angles here, this angle and this red angle. These 2 red angles must be the same because, again, A, B, C, P are concyclic. So one angle added to this is to 100 degrees, so it has to be equal to the exterior angle. So these 2 red angles are the same. And when the red angles are the same, then the 2 blue angles must be the same because they are supplement to the blue angle. They add up to 90 degrees. Okay, so therefore these 2 brown angles are the same. That is the proof of Simpson line. Okay, Simpson line has a lot of properties, and if you are interested, we can talk about this later. You can also go to the gdp.mass.uci.edu to take a look about topic 5 with a comprehensive introduction to the Simpson line. Okay, so what I like the most a lot is that I'm going to use the Simpson line to prove the Ptolemy theory. How? Here's the trick, right? We have A, B, C, P that are concyclic, so you can take this as another point of view. So P is a point on the circumcircle of the triangle ABC. So by the Simpson Theorem, so the projection of P to the three sides, x, y, and z respectively, has to be collinear, what I draw. Okay, so again, zx will be equal to zy plus yx. And you may already have expected that I can use trigonometry, using whatever way, to compute the length of three of them and add them up. Okay, so what is zy, by the way? So zy. Okay, so these 4 points, as I keep saying, the 4 points, this guy, this guy, this guy, this guy, they are concyclic. And since this is the right angle, so the AP is a diameter. AP is a diameter. And once AB is a diameter, so the law of sine tell you that zy is equal to, well, the diameter AP times sine, sine BAC. Okay, why? Because this is corresponding to that, but this angle is equal to that angle. So this is equal to sine BAC. Sine ZPY, but sine ZPY will be equal to sine BAC. Okay, so here I'm going to use the fact that BAC is basically angle A of the triangle. And I use the law of sine again with respect to triangle. That will give us BC over AR. So just keep in mind that this is what I wanted. And we can do the same, using the same method to compute both yx and zx. And I add them up. And once I add them up, so I cancel 2r. So that gives us the proof of the Ptolemy Theorem, because AC and the BP are the two diagonals. BP is a diagonal, AC is another diagonal of the quadrilateral ABCP. And so APBC are the two opposite sides. The two diagonal, it would be CP and the CP and the AB. I mean, the other two sides is CP and the AB, two opposite sides. APPC are the two opposite sides, and the AC times BP is the product of two of them. Okay, so the product of two diagonal. Okay, so this implies Ptolemy Theorem. Can we use that to prove the Ptolemy inequality? I don't know. We can certainly think about that. Okay, so that's all for today's talk. You will have an opportunity to practice both Ptolemy Theory, Kelvin Transform, and Simpson Line in the exercises. Thank you.